Today we're going to be talking about probability distributions, and then we'll go on and talk about binomial probabilities and binomial probability distributions. We're going to start today with a pretty simple experiment, and we're going to look at the outcomes and the probabilities and the probability distribution. So the experiment we're going to start with is to just roll one die and record the number on the face. This is a normal six-sided die with the numbers 1 through 6 on the face. When we create a probability distribution, this is going to look a lot like the frequency distributions we did in Unit 1. One of the differences is that for the outcomes, this is going to be a variable. We usually call this x. This is what a random variable is. Random means that it has something to do with probabilities. The entries in this list under outcomes have to be numerical. This is one major difference between the frequency distributions that we did in last unit and the probability distributions that we're doing now. For a valid probability distribution, the outcomes, the values of x, have to be actual numbers. They can't be in words. The next column is going to be probabilities. These can be in fraction form, in decimal form, or they can even be listed as percentages. But for most of what we're going to do here today, we're either going to list them as fractions or as decimals. So let's look at our experiment and first of all write down what the different possible outcomes are. Since this is a normal die with 6 faces and the numbers 1 through 6 on each face, that means those are our outcomes. So our outcomes, or our possible values for x, are the numbers 1 through 6. To fill in our probabilities, we know we've got 6 faces. If we assume that this is a fair die, then each one of the faces is equally likely to come up. We've got a total of 6 possible outcomes. So the probability for each one is going to be 1/6. And for each one of these, we could put it as a fraction, or we can put it as a decimal rounded to 4 decimal places. So this is going to be the same for every one of these. So here's our probability distribution. We've got numerical values for our variable x, and we've got the probabilities for each one. Now, two things about the probabilities for this to be a valid probability distribution is that all the probabilities have to be between 0 and 1, or if we were doing this in percentages, they'd have to be between 0 and 100%. Also, the probabilities have to add up to 1, or 100%. So if we added all these up as fractions, then this would come out to be exactly 1 for the total. If we add up our rounded values in decimals, then it's going to be not quite 1. It's going to be something like this. So because of the rounding here, we would get a little bit of rounding error if we added up the decimal values. That's close enough to 1 for us to assume that it actually would add up to 1 if we hadn't done the rounding. Now, another thing that we can do with probability distributions is we can create a histogram, or a graph. That gives us a picture form of what the distribution looks like. I went out to StatCrunch and created a histogram, had it do the relative frequencies, so it's giving me the same thing as the probabilities here. So this is what it comes out looking like. We've got our 6 different possible outcomes, and since each one has the same probability, this is just even all the way across. This is what we would call a uniform distribution. The next thing we're going to do is try to find the expected value, which is the same as the mean of the probability distribution. This is a little bit different than the means we talked about in Unit 1. What we're doing with the mean for a probability distribution is that we're not just looking at the average of all the outcomes, but we're weighting that by the probabilities. So this is like a weighted average or a weighted mean. In this case, since all of our probabilities were the same, our mean is actually going to come out to be just the same as what we would get if we did the average of our outcomes. So if we took 1 through 6 and added all those together and divided by 6, That would also give us the mean for this probability distribution. But that's only because all of our probabilities are the same. The way we would normally do this for a probability distribution is that we would take each of our numerical outcomes, multiply it by its corresponding probability, and we would make another column in the table for those results. If we add up those results, the total for that column would be our mean. So here we take 1 times 1/6. We would just do this for each one of these. And I'm just doing this with the fractions because then we don't have to deal with the rounding error. We would go ahead and multiply each of these together. And when we got all this done, we would add all those together. This actually adds up to 21/6. Which if we go ahead and divide that, that turns out to be 3.5. So this is our mean, or our expected value. And in this case, it's the same thing we would get if we just added up the numbers from 1 up to 6 and then divided that by 6. So our expected value is 3.5. The next question is, what does this expected value, or the mean, tell us? Well, for one thing, if we're thinking about these outcomes being data, then the mean should give us where the center of the data is. And you can kind of see that in the table. Since we've got these outcomes from 1 through 6, our mean ought to be exactly halfway between those two. And again, that's just because all of our probabilities are the same. But we could kind of guess that our mean would be exactly halfway between 3 and 4. One thing this would tell us is that the center of the data is at 3.5. If we're thinking of this as an expected value, that means the value that we would expect to get as an average if we repeated this same experiment many, many times. So our expected value is what we would expect to get as an average of the results after we repeat the experiment many, many times. So if we rolled a die 200 times or 500 times or 1,000 times, and we wrote down the result each time and then we averaged those, we would expect to get an average of 3.5. And the more trials we do, the more times we repeat this, the closer we would expect our actual average to be to our expected value of 3.5. Okay, now let's think about one more thing to do with the mean. If we look at our probability histogram, if we were just looking at this and trying to figure out what the mean would be, it looks like it would be at 4. Yes, the probability histogram is misleading, so it makes it look like the mean is 4 instead of 3.5. Then the next question is why. The reason is that in this case our values are all discrete values. This histogram is making it look like we've got continuous data. So here we've got a class that goes all the way from 1 up to almost 2. And notice our last class, it looks like starts at 6 and goes all the way up to almost 7. So it's kind of skewing it towards the right because it's including these bigger numbers that actually aren't happening in our graph. Another way that we could do this that would be a little bit more helpful would be to just do this as a bar graph instead of as a histogram. So I went back to StatCrunch and did this as a bar graph, and this way it's representing each different outcome as a separate bar and it's putting gaps in between. And if we look at it this way, we could pick out pretty quickly where our mean is. Because each of these is the same width, our mean would be, or the center of our data would be exactly halfway between these two bars. So the very middle of this graph would be at 3.5. Now let's look at another experiment. This time, instead of just rolling one die, we're going to roll 2 dice, and then we're going to add the 2 faces together. So the experiment is to roll 2 dice and record the sum of the faces. First of all, we have to figure out what the different outcomes for this experiment would look like. So I set up a little table So we've got the first die and the second die. We're going to take those and add them together, and I'm going to fill this table in with all of those results. So this row starts with 2. This row starts with 2 plus 1, which is 3. So I'm just filling in this entire table. So there are all of our possibilities for how the 2 die can come up, and then for each one I put in what the sum of the 2 die would be. We filled in this whole table with the sums from the dice, and now we want to look at what different outcomes we have in this table so that we can do a probability distribution for those. So if we look at the different values that we ended up with, we have a 2, a 3, a 4, a 5, a 6, a 7, and all the way up to 12. So those are all of our different outcomes. Now for our probability distribution, we want the probabilities for each one of those. And for that, we have to go back and look at what was happening here. We had the one die being rolled and the second die being rolled, and those were both, each outcome on each die was equally likely. What we ended up with was these 36 entries in this table up here, since we have 6 rows and 6 columns, and each one of these entries would have been equally likely. So we can figure that each one of these entries in this column, the probability of it would be 1 over 36. And that's what we can use to get the probabilities for our different outcomes. All we're going to do is take the outcome, see how many times it comes up in the table, and then we're going to have that number over 36 for our probability. So for the 2, that only comes up once, because the only way that can happen is if both dice are a 1. So the probability for this is just going to be 1 over 36. Then for the 3, that happened twice in the table, so that probability is 2 over 36. And I'm just leaving these, I'm not trying to reduce fractions or anything because we're going to put these in a decimal form anyway. For the 4, there are 3 4s in our table. For the 5, there are 4 of those. For the 6, there are 5. And for the 7, there are 6. Now looking at this pattern, you might think that this is just going to keep going up, but actually what happens is when we get above 7, it starts coming back down, because if we look at the 8s, there are only 5 8s. So that probability would be 5 over 36. For 9, it's 4 over 36. So what ends up happening is this goes back down to where when we get to 12, it's back down to 1 over 36. Now I'm going to go back for each one of these and put in a decimal approximation. So I'm going to take these and round them to 1 decimal place. Now I have all of these probabilities filled in. So this gives me my probability distribution because I have all of my outcomes as numbers and I have the probabilities for each one. I could check my probabilities by adding them all up. If I do that, I'm going to get 1 if I add it up with the fractions, and if I add up the decimals, it might be just a little bit off because of rounding error. But it's going to be close enough to 1 just for me to be able to check and make sure that those are right. Now what we can do once we have this probability distribution is we can look at a graph. And again, I did a bar graph instead of the histogram because this is actually a little bit more accurate when we've got discrete values for our outcomes. And from this bar graph, you can see pretty easily how symmetric this distribution is. It's symmetric. It looks kind of bell-shaped because it does start out low on each end and then it has a high point in the middle. It's definitely symmetric. The other thing that we could tell pretty easily from looking at this graph is where the center of our data is, and that would be at 7. That's the highest bar, and it's exactly in the middle of all these. Now what we're going to do is look at a simulation of this experiment and just see what happens as we do more and more trials of the experiment. So here's a little simulation. What this one will do is it'll do 10 rolls at a time. I'm going to start out by doing 50 trials and just see what that looks like over here. So here's our result in the simulation when we do 50 trials. And of course this isn't going to be exact as to what we were expecting, but it does have some of those properties we were kind of expecting to see. This one, it turned out that the 7 has the highest frequency. The 6 and the 8 on either side are pretty close to that. And then it goes down on each end. And actually even the 2 has a frequency of 0. So I'm going to put these frequencies in here. There are all of our relative frequencies. Again, if we added those up, those should add up to 1. Now we're going to do the same thing, only I'm going to do a bunch more trials over here so that I end up with 200 trials. And we're just going to see what we come up with. And then here, if we do the relative frequencies, now we're going to look at our probability distribution that we filled out and compare it to what we got. So these over here would be the classical probabilities. These ones over here would be the empirical probabilities, or just the relative frequencies. And again, the ones, even with the 200 trials, it's not exactly like the probabilities that we had over here, but it's certainly a lot closer than what we had in this one when we only had 50 trials. If you look at this one with the 200 trials, some of these are actually fairly close to the classical probability. So for instance, for the 2, we've got a 0.025 versus a 0.0278. For the 3, it's pretty close. For the 4, it's not so much. For the 5, it's not so much. The 6, it's pretty close. Anyway, the point is it's getting closer as we do more trials. And as we could go through and keep doing it with this program, or we could clear this and do this again. The thing about this is that each time you go through this, you're going to come up with a different result because it's a different sample. And that's one thing about this when we're talking about probabilities. It's all about what's likely to happen. That doesn't mean that's what's going to happen. Even the things that are very unlikely still are possible to happen. Unless the probability is actually 0, then even if it's really small, it's still possible that it could happen. And just because something is really likely doesn't always mean that that is what happens. So for instance, this time around with my 50 trials, I got the 6, 7, and 8 all happened 9 times. So this one, again, looks kind of like the probability distribution that we were expecting. And as I go up to more trials, it's looking more and more like that distribution that we were talking about. Now we're going to look at a different experiment. In this one, we're going to play a game. We're going to use a spinner that's half blue, 1/3 red, and 1/6 yellow. And we've got a simulation for this one too. So here's our simulation. This is kind of the same thing. It'll do 10 spins at once for you if you ask it to. But before we start doing that, let's look at how we would write our probability distribution. I've got this filled in already with just the colors and the probabilities for each one. But if we want to make this a valid probability distribution, we need to fill in some kind of numerical values for the outcomes. This still gives us an idea of what happens. We can still use this table, but it doesn't actually count as a probability distribution unless we have numerical outcomes. So what we need here is numerical outcomes for x. X is our random variable. What we're going to do, if we want to treat this as a game, is that we're going to say that depending on which one of these outcomes you get, that you're going to win a certain amount of money. For right now, we're just going to say how much money we win. We're not going to worry about any situations where we lose money. Let's say that for the blue, that you would win $1. And that for the red, that you'd win $4. And for the yellow, that you would win $7. Now we've got some numerical values that we can put in for our x. Now how we put these in depends on whose point of view we're looking at this from. Right now we're going to look at this from the player's point of view. So if I'm playing this game, I'm going to put these outcomes as that I'm winning money each time. That means my outcomes here are going to be positive numbers. So I have a +1, +4, and +7. To make sure that this is a valid probability distribution, I would want to make sure that my 3 probabilities do add up to 1. And if you go through and add the fractions, yes, they do add up to 1. The probabilities have to add up to 1, and also they all have to be between 0 and 1. So those all fit. There's no condition on the values of x except that they have to be numbers. So they can be negative or positive, and they don't have to add up to anything in particular. For this one, if we want to find the expected value of the game, that means we'd find the expected value or the mean of the probability distribution. So this is where we're going to do the x times the p of x. This one's going to be a little bit different because we don't have all equal probabilities. So these aren't all just 1/3, they're all different. So the blue is going to get weighted a little bit more because that has a higher probability than the red, and the yellow is going to get weighted the least because it has the smallest probability. So when we do this, we're just going to take 1 times 1/2 here, which gives us 1/2. Here, this is going to be 4 times 1/3, and this one's going to be 7 times 1/6. So to get our mean, or our expected value, we're going to take those 3 results and add them together. That's going to give us 18/6, which is 3. So from the player's point of view, the expected value is $3. What that tells us is that if we were going to go and play this game a whole bunch of times in a row, this is the average amount of money we would expect to win per play. The answer to this is that we would expect to win an average of $3 per play, played this game many, many times. The expected value is always about what's going to happen in the long run. In the long run, if we played this game 100 times or 1,000 times, and then we went back and added up all our results, that the average amount we'd win per play would be $3. Now that doesn't mean that we're winning $3 on any one play. We can't, because that wasn't how our game was set up. We're either going to win $1 or $4 or $7. We're never actually going to win $3. That's just the average per play. Now once we know that, we could figure out how much money we could expect to win if we played this game 30 times. So in 30 plays, if we're averaging $3 per play, 30 times 3 would be $90. That doesn't mean that every time we're going to win exactly $90, 30 plays. It just means that's how much we can expect based on the probabilities. And for 100 plays, then we'd just be taking 100 times our average per play, which would be $300. Now let's go over here and actually do this a few times. I'm going to set this to 10 so that I don't have to spin a whole bunch of times in a row. So what we came out with here, in 30 spins, we actually got blue 15 times, which is exactly half of the time. That one came out to be exactly what we were expecting. For the red, we got 12 out of 30, which is a little bit more than 1/3. 1/3 would have been 10 out of 30, so we got a little bit more reds than we would have expected. And for the yellows, we got a couple less than we would have expected, because 1/6 of 30 would have been 5. So this is close to what we were expecting, but we wouldn't have gotten quite as much as $90 because we didn't have quite as many yellows as we would expect. In our actual simulation, 15 times $1 plus 12 times $4 plus 3 times $7. For those 30 plays, we would have only come up with $84. Not quite as much as our expected value, but it's still in the same ballpark. Then I'm going to do this a bunch more times so that we've got 100 spins. Here's what happened when I did 100 spins. So I got 54 blue ones, which is a little bit more than half. My winnings would be 54 times $1. I have 32 red ones, and that's almost 1/3. 1/3 would be about 33, so that's pretty close there. And then I have 14 yellow ones. So my winnings there turned out to be $280. Again, on this one it was a little higher on the blue and a little bit lower on the yellow than we were expecting. So that's why the winnings aren't quite as much as what our expected value gave us. But this is a good example of the difference between the expected value based on the theoretical probabilities and what actually happens. Since this is a game of chance, anything can happen technically. We're just talking about what's the most likely thing to happen. Now let's do one more variation of this. If we make this into an actual gambling game where we could lose money, one way to do that is to make the player pay $4 before each play. Let's look at how that would change our outcomes and our expected value. So this time, if I'm playing, I've already paid in $4 before I play. If I get a blue, then I win $1. So that means I put in 4, I got back 1. I've actually lost $3. So to signify that I lost the money, I'm going to put this in as a -3. So this time this is going to be, instead of just how much I won, this is going to be my gain or loss on the play. A loss I'm going to put in as a negative number. If I get a red, then I put in my $4 and I would get back $4. So that means I broke even. My gain or loss is 0. If I get a yellow, I put in $4, I got back 7. So that means I won $3. My net gain was $3. So there are my values for those 3. Now if I want to figure out my expected value, I'm going to take each of these and multiply them together. Now I have to be careful here because if I have a negative value over here, I have to make sure and include that when I do this. So this is going to be -3 times 1/2, which is going to give me a -3/2. This one is 0 times 1/3, which is going to give me a 0. This one is a +3 times 1/6. That's going to give me a +1/2. If I add these 3 together, the -3/2, the 0, and the 1/2, that's going to give me an answer of -1. This means that my expected value is a -$1. What this means is that I can expect to lose an average of $1 for each play. This time, if I played this game 30 times in a row, that would mean I'd expect to lose about $30. If I played it 100 times in a row, I'd expect to lose about $100. If we look at this from the operator's point of view, that just means that our gains and losses are going to be switched around. So I just copied this table down here, but from the operator's point of view, the person paid me $4, and if they landed on blue, I only give them $1 back. So I've actually made $3 on that. For red, I broke even. For yellow, that means they gave me $4, I had to give them 7 back, so I lost $3 there. And that changes this to a positive and this to a -3. So all that does is it changes my mean from a -1 to a +1. So for this one, the expected value from the operator's point of view is a +$1, which means that the operator can expect to make an average of $1 per play. This is exactly how casinos and gambling games make their money. They might not be making a lot per play, but they're dealing with thousands and thousands of repeats of a game that's being played. Even if their expected value is only a little bit of gain per play, still in the long run they're going to end up making a lot of money. In this one, if we had 100 people that came up and played this game, if we're the operator, then we could expect to make about $100 from those 100 plays of the game.